Now, we develop a new concept called metric tensor. So, let us try to take dot product of two vectors r and s. R has components r 1, r 2, r 3 and S has component S 1, S 2, S 3 and we are in real space. So, we are in the crystal basis. So, what is R dot S? The dot product R dot S in terms of component. So, R 1 S 1 plus R 2 S 2 plus R 3 S 3, dot product of two vectors in terms of components. Yeah, this is our familiar dot product. This formula at least you should know before the course. Yep, no confusion, we can proceed. Only thing is that this is not right, this is incorrect, that is why I was giving you time, because this is only for, this is true only for Cartesian system. I told you that this is in real space. Real space means the crystal space, and these are with respect to the crystal basis. In crystal basis, if they are in crystal basis, what can you say about R? R now means R 1 A, crystal basis is A B C. So, whenever we say components, components with respect to a given basis. So, when the basis is A B C, the components R 1, R 2, R 3 is with respect to that basis, which means the vector is R 1 A plus R 2 B plus R 3 C. And similarly, the vector S is S 1 A plus S 2 B plus S 3 C. Now, if you take the dot product R dot S, you can see that you have to take a dot product like this. 3 terms in each bracket, there will be 9 terms. 3 into 3, 9 terms. So, you will have R 1 S 1 A dot A, R 1 S 2 A dot B, R 1 S 3 A dot C plus R 2 S 1 B dot A, R 2 S 2 B dot B, R 3 S 3 B dot C plus R 2 S 3, R 3 S 1 R 3 S 1 C dot A, R 3 S 2 C dot B, R 3 S 3 C dot C. We are stuck with all these 9 terms, we can't get away with that. You can see, unless and until alpha, beta or gamma one of them is 90 degree, none of these dot product is going to vanish. thanks to Cartesian system, orthogonal system, where all three angles are 90 degree. So, all non similar dot products A dot B, A dot C, B dot C all vanish. So, 6 terms out of these 9 terms vanish, only the diagonal terms A dot A, B dot B and C dot C survive, but that is the property, that is the beauty, and that is the power, and that is the reason why Cartesian system is so much favored. But in crystallography, once we have decided that our unit cell is A, B, C, alpha, beta, gamma, that is the lattice parameter, it may happen that none of these dot products is 0. So, we are left with all these 9 terms. Only way now to simplify this available to us is to write it in a matrix form like this. We can take the 2 component vectors r1, r2, r3, one of them as row vector, one of them as column vector, and in between write a matrix G which has this form: A dot A, B dot B, A dot A dot B, A dot C, and so on. It is a symmetric matrix, you can see. And this equality you will have to work out and see. If you write this matrix, open this out, you will find that you get the same 9 terms. So, the advantage of writing it in matrix form, first of all, is that it makes it little compact rather than writing it as 9 term sum there. You write it in a matrix form like this. The other advantage is that it abstracts out those terms which are depending on the lattice parameter, which is the G, the metric tensor, and those which are the components of vector, which does not depend upon the lattice parameter, which can be anything. So, r1, r2, r3 are component of one vector, s1, s2, s3 component of another vector. They are variables, but once a particular unit cell is selected in a particular crystal, then this A dot A, A dot B, this metric tensor is fixed. So, this is what is known as the metric tensor and gives you, is used for calculating dot product in a general non Cartesian coordinate system. How do we calculate this G from lattice parameter? It is very simple. Look at the definition. The terms of G are just A dot A, A dot B. The first term is A dot A. What is A dot A? A dot A is A square. So, that is the square of the first lattice parameter. G12, which is same as G12, G21 is A dot B. What will be A dot B? Length of A, length of B, cos of angle between A and B, which we have called gamma. So, it is A B cos gamma. G13 A dot C. So, A C cos of angle between A and C, which is beta. G22 B dot B, B square. G32 B C cos alpha. G33 is C square. C dot C is C square. Maybe here also we can write B dot C and then write B C cos alpha. So, the metric tensor is, once we know the lattice parameter, metric tensor calculation is not difficult. In terms of lattice parameter, all the 9 terms or all the 6 independent terms of the metric tensor are functions of the lattice parameter. So, given any lattice parameter, you can calculate the metric tensor. Now, how does this reduce to the orthonormal basis? You can see that for orthonormal basis, A, B and C are the 3 unit vectors E1, E2 and E3, and they are orthogonal. So, here you will have E1 dot E1, E1 dot E2, E1 dot E3, E2 dot E1, E2 dot E2, E2 dot E3, E3 dot E1, E3 dot E2, E3 dot E3. But knowing the property of this unit this vectors, you know that this will become 1 0 0 0 1 0 and 0 0 1. So, that means the metric tensor for orthonormal basis is nothing but identity. So, now if you use that in the general formula where you had R1, R2, R3 multiplied by the metric tensor multiplied by S1, S2, S3, but the metric tensor now is I, and I obviously does nothing. It leaves I times S1, S2, S3, S1, S2, S3. So, you get R1, R2, R3 row vector multiplied by S1, S2, S3 column vector, which gives you the normal dot product formula with which we had started. So, you have simply generalized the dot product for a more complicated coordinate system, that is all. Other things just follow. So, if you want to find length of a vector in a crystal coordinate system, so you have the vector like this, the length will again be the dot product of the vector with itself will give you the square of the length. Only thing now you have to write the components with G matrix coming in between. So, that will become your R square. If you insist on R, then you can take the square root of this quantity. So, the row vector UVW multiplied by the metric tensor, sometimes called metric matrix also, metric matrix or metric tensor, same thing. So, that is the length of the vector. The angle between two vectors, again you know R dot S is R s cos theta, where theta is the angle between R and S. So, that becomes this, and just using the formula which you had derived now. So, it will become R1, R2, R3 into G into R1, R2, R3 sorry, this is R dot S. Oh, yeah. So, this is R dot S. So, this side will be the S vector, S1, S2, S3. So, that is the numerator, and the length R will be R1, R2, R3 times G times R1, R2, R3 square root, just like we saw. So, means writing it by hand is a little messy and complicated, but you can program it in computer and give any lattice parameter or any components. You can easily find the angle between vectors or length of a vector, even though now you are working in a system which is non-Cartesian. So, crystallography just forces you to generalize yourself, come out of your comfort zone of orthonormal Cartesian basis. But it is as you can see that once you have this metric tensor, the discomfort is not so much, you can still calculate everything. So, coordinate now we have seen the coordinate transformation in the real basis. Now, can we do that same thing for reciprocal basis? So, let us see this. What we want to do, we have seen that we have developed this formulation partially and the rest was left as a homework exercise for you, the last column, that ABC, if you have ABC as your given basis and you want to go it into the Cartesian basis E1, E2, E3, you use the matrix C. Now, suppose you have the reciprocal basis, the corresponding reciprocal basis A star, B star, C star. How can you go into the corresponding Cartesian basis? So, that will be the matrix C star. Now, how did we write C? We expressed A, B and C as column vectors in Cartesian coordinate system. So, A1, A2, A3 are the first column of the transformation matrix C is A1, A2, A3, which is nothing but components of the first basis vector, first crystal basis vector A in terms of E1, E2, E3. So, it is the Cartesian components of A. The second column is Cartesian components of B, third column is Cartesian component of C. Now, we do means this is not necessary, but this convention is used in international tables. So, we want to follow this, that we decide to write reciprocal lattice vectors. This is important, this is just a convention. You can violate this and decide that I will write the reciprocal lattice vectors also as column vectors like I was doing for the real basis vectors. But some simplicity comes if you write the reciprocal basis vectors, reciprocal vectors as row vectors. So, coordinate transformation of the reciprocal basis will be represented by, now suppose this was the coordinate transformation matrix. So, you multiply that to the untransformed components. HKL is component of a vector in reciprocal space. H star, K star, L star is components of the same vector in a new basis. So, now you have two reciprocal bases. You have A star, B star and C star. You also have A star prime B star prime and C star prime. So, HKL is with respect to this yellow basis. HKL is with respect to A star, B star, C star. H star, K star, L star is with respect to the new basis. A star prime, B star prime and C star prime, which means the same vector. If I draw a vector, let us say this vector. So, this vector is being expressed as HKL when I use the yellow coordinate system and is written as H prime K prime L prime when I am writing it in terms of the red coordinate system. And how do I go from one to other? So, since I decided to write them as row vectors, so the row vector multiplies the matrix from front, as you know, from the left. So, I have written it in terms of the left vector, and if you take the HKL as 1 0 0, you can say this, then what will you get? 1 0 0 will multiply with C1 1 star C star matrix will pick out 1 0 0 will pick out the first column, sorry, first row. This will pick out the first row. If you multiply this with 1 0 0, it picks out the first row, which means the first row of the transformation matrix is nothing but A star transformed into orthonormal basis, because RHS is the vector in orthonormal basis. I was little bit negligent in drawing my primed coordinate system. I made it very general, but if I am writing the C matrix, I am assuming that I am transforming it to an orthonormal basis. So, you have to allow for A star, B star, C star. You have assume that A star, B star, C star is orthonormal and not general. So, the first row is A star expressed in orthonormal basis and so on. The second row is B star expressed in orthonormal basis. The third row is C star expressed in orthonormal basis. If that is the case, we can derive an important property. Let us say C star C. This product, let us take the product of these two matrices, C star C. So, C star has A1 star, A2 star, A3 star. This was C star. So, A star expressed in E1, E2, E3. So, I am saying A star has a components A1 star, A2 star and A3 star. B star has component B1 star, B2 star and B3 star. C star has component C1 star, C2 star, C3 star. This is what we get for C star. C we have seen that we write as columns of A, B and C. So, this is the components of A, A1, A2 and A3. These are the 3 components of B, B1, B2, B3. These are the 3 components of C, C1, C2, C3. Now you can use this property of the first row is A star expressed in Cartesian coordinate system. First column is A expressed in Cartesian coordinate system. So, when you multiply C star C, and let us take a particular component, let us take 1 2 component. So, that is first row multiplied by second column, let us say. So, that will be A1 star B1 plus A2 star B2 plus A3 star B3. In Cartesian components, term by term dot product and sum is what? Is just the dot product of A star and B. This is the dot product of A star B. So, the 1 2 term is just the dot product of first vector A star and second vector B. So, similarly, you can write the entire matrix C star C, the 1 2 term we just worked out, currently 1 2 term as A star I am using little bit of confusing terminology here. So, let me write it out completely. So, C star dot C these 9 terms, the 1 2 term we worked out as A star B. The 1 3 term if you work out, it will come out to be A star dot B, A star dot C. Similarly, this is A star dot A. Then you will have B star dot A, B star dot B, B star dot C, C star dot A, C star dot B and C star dot C. But then by definition of the dot products of real and reciprocal vectors, only A star dot A, the diagonal terms will be 1, the off diagonal terms will be 0, which means C star C is identity. That simplifies our life a lot, that we do not have to calculate C star separately. If we have calculated C, the transformation matrix for the direct basis to a Cartesian basis, C was transformation matrix for direct basis to Cartesian basis, then the transformation matrix for the corresponding reciprocal basis to the same Cartesian basis is nothing but the reciprocal of the direct transformation matrix. This relation will be important in establishing some other relations. So, let us look at that. Let us find out what is C transpose C. So, C we just saw that C has columns of A, B and C expressed in Cartesian coordinate system. So, C transpose will have rows expressed as just the transpose of the previous matrix. So, now the basis vectors are written as rows. And if I multiply again, say let us again calculate 1 2 term, or let us try to do some other term 2 3 term. So, we take the second row and multiply it with the third column. So, what do you get? A 2, A 3, B 2, B 3, C 2, C 3. But this is A 2, B 2 and C 2 sorry, I multiplied it wrongly. So, let us get rid of this because transpose comes first. So, I should take this matrix first. So, I this is C C transpose. So, let us do that again. C transpose C 2 3. So, I take the second row here and multiply it by third column from this matrix. So, B 1 C 1 B 2 C 2 plus B 3 C 3. Second row from here multiplied by the third column here. This is B 1, B 2, B 3 are components of the B vector, and C 1, C 2, C 3 are components of the C vector. So, this is nothing but B dot C. Okay. So, similarly, you can see that CTC matrix we just calculated the 2 3 terms. So, second row third column, this was B dot C. By same analysis you can keep working out, you will find that this is A dot B, sorry, A dot A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B and C dot C. Some algebra is there and some thinking is required. So, you have to do that on paper yourself also, because I can see that in lecture it is not a very easy way to communicate, but all I can do is to work it out with you. So, you get this matrix, but what is this matrix? This should now be familiar to you. Yeah, but we defined it as some matrix just in this lecture, the G matrix, the metric tensor. So, this is the metric tensor. Which we called G. So, is an interesting way of getting. Yeah.
How did we write the dot product?
This one,
Yes.
2 3, the 2 3 term.
Yes.
In the transpose matrix, the second row is B 1, B 2, B 3. That is the components of the basis vector B in Cartesian coordinate system, because C is transforming the basis vectors to Cartesian system. Okay. So, B 1, B 2, B 3 are components of B, C 1, C 2, C 3 are components of C in Cartesian coordinate system, where the dot product has this simple form B 1 C 1 plus B 2 C 2 plus B 3 C 3. Despite all our problems with metric tensor, in Cartesian the metric tensor is identity. So, that is not appearing here. So, this simply becomes B dot C. So, just like now I am taking a jump of faith that just like 2 3 became B dot C, 1 1 will become A dot A, but you can check that and it is not that difficult, and 1 2 will become A dot B. So, that the whole matrix C t dot C, the product matrix, that becomes the metric tensor. So, this is an interesting relation. We stop here, the time is up. So, this is an interesting relation that if you have the transfer, we wrote, let us see, we wrote very different things. So, in a sense the relationship is interesting and I will say to some extent surprising also, because our metric tensor was a tensor defined in terms of the basis vectors. It has nothing to do with Cartesian coordinate system. It was not asking for any Cartesian coordinate system. A, B and C were 3 vectors, totally non-Cartesian, totally non-equal, angles not equal. So, the set of dot products was the metric tensor. The set of dot products written in terms of this matrix is the dot product. C had to do something with the Cartesian coordinate system. C was taking A, B and C to Cartesian coordinate system. But then now we find that if we have that transformation matrix, if we have that transformation matrix, then the transpose of the transformation matrix multiplied by the matrix itself is nothing but the metric tensor. So, this is a great result, I will say, nice result, despite appearing to be quite boring during the lecture. This is a nice result, establishing the relationship between the two matrix. So, okay, thank you very much.